The speaker of the first talk is Bilge Acun from Facebook AI Research or FAIR, and she is working on making large-scale machine learning systems more efficient through algorithmic and system optimization. She received her PhD from UIUC, and before joining Facebook or Meta, she worked at IBM Research, and her research interests include systems for machine learning, parallel and distributed computing, energy efficient computing, high performance computing, and smart runtime system. And she's going to talk about a holistic approach for data center sustainability. Thank you, and go ahead.
Thank you very much for the introduction. So as Mohammad mentioned, I'll propose a holistic approach for data center sustainability in my talk today. So starting with the big picture, data center energy footprints are growing. And looking at the energy consumption of some of the biggest technology companies over the last 5 years, we see that the energy footprint of Microsoft and Google has grown about 2 times and Meta close to 4 times. So this plot is normalized to show the growth. And if you look at the absolute energy usage, and that's shown in the labels on the blue bars, Microsoft consumed 6.3 terawatt hours, Google 7.6, and Meta 2.4 terawatt hours. And currently, data centers consume 1 to 2% of the global energy demand and 30 to 50% of the ICT's total energy footprint. And ICT energy consumption is projected to reach 7% by 2030. And a significant portion of this growth at Meta's data centers is driven by AI. AI models have grown thousands-fold in the last decade, and they continue to grow. And to reduce the footprint of AI, we work on efficiency improvements, such as using different AI models and algorithms. And such algorithmic changes are really powerful. And looking at the recent history, we see that most energy efficiency increase in machine learning is coming from algorithmic improvements. And OpenAI recently published that there was 44 times improvement in training ImageNet in the last 7 years. And in contrast, the innovations in systems and hardware enabled only 11 times efficiency improvements. However, these improvements does not actually reduce the energy footprint of the AI models or data centers at large. And this is due to Jevons paradox, which suggests that efficiency also increases consumption. As we improve the systems and algorithms, they become more prevalent and overall usage increase. So we need to design our data centers with sustainability in mind, considering the carbon footprint of the hardware from the start to end of its life cycle. So first, manufacturing, which starts from extraction of the raw materials used in the hardware, then transport, use of the hardware, and finally recycling at the end of its use. And most of the existing research focuses on product use, but we need holistic approaches which considers both embodied and operational use. So let's take a look at the breakdown of embodied versus operational carbon footprint of AI models at Meta. As you can see, majority of the footprint is operational, and data centers usually offset the operational parts and claim carbon-free. When you do that, the embodied carbon you inherit when you buy servers and the data-centered hardware becomes significant. Offsetting carbon for operational use is great, but it doesn't solve the problem in long term. Because with carbon offsets, you purchase the renewable energy generated elsewhere, which may be generated at a different time of the day and used by someone else, while you continue to use the energy from the grid of the data center. So, so we need to, in the long term, we need to learn how to operate fully on renewables. So shares of renewables in the US grid is projected to grow from about 20% to 42% in 2050, and 81% of the renewable energy will be solar and wind. On the right, you see California grid's renewable energy generation from a selected week, showing that there's high variability in energy generation as much as 3 times. And as the renewables in the grid increases, we are going to see more and more fluctuations in energy generation, and we need to learn how to deal with this variability in the long term for data centers. In fact, renewable fluctuations are already causing curtailment problems in California grid. And this is because of transmission bottlenecks and oversupply issues. The curtailed renewable energy has grown steadily as wind and solar capacity has increased. And last year, 6% of the total generated renewable was curtailed. So how can we design data centers to operate on renewable energy at every hour given this variability? First, data center operator needs to decide the solar and wind investment amount, which will generate a certain energy profile. And this may leave gaps in your renewable supply as shown in the figure here. Then we need to implement complementary solutions such as energy storage or computation shift. So while doing these, we need to consider renewable energy characteristics per region. So the renewable energy characteristics affect the data center site selection decisions as well. So I will propose and present you a framework called Carbon Explorer that we are actively working on building to solve these problems. And the goal of the framework is to help evaluate solutions to make data centers operate on renewable energy. And Carbon Explorer takes supply and demand data as inputs, evaluates potential solutions using the input data, and produces carbon optimal footprint curves as outputs. So as inputs to Carbon Explorer, we need fine-grained data on hourly data center power load and renewable supply per region. As solutions, we evaluate 3 different solutions: renewable deployment amounts, battery deployment in data centers, and carbon-aware scheduling, which means shifting the workloads from times when there's renewable supply is abundant to times where there's excess supply. And as an output, Carbon Explorer will find the carbon optimal solution by taking into account both operational and embodied footprint. So we will deep dive into each solution later, but first let's start with the inputs we need. Meta has many data centers across the US as marked on the map. And here are the wind and solar farms Meta helped build close to data center regions marked as green and yellow points. So we need to generate the supply and demand profiles for each data center, and we do this by taking EIA's hourly grid monitor data. Next input we need is the hourly data center power demand. Data centers exhibit daily load fluctuations. Top right plot shows that the CPU utilization of Google and Meta data centers varies at different hours of the day. On average, the daily swings are about 15 to 20%. On the right bottom, we model the relationship between utilization and power, and that daily 20% utilization swing corresponds to 5% power swings daily. So data centers consume more power during the daytime, but fluctuations are not nearly as significant compared to renewable energy fluctuations. And Carbon Explorer uses the hourly power load of data centers as inputs to the framework. So let's deep dive into the solutions now. First, we need to determine the optimal renewable investment amount for each of our data centers. As deployments increase, hourly renewable coverage increases, but manufacturing footprint coming from building the solar and wind farms also increases. And there's the problem of, and this causes excess supply. So these charts show the renewable coverage, which means the percentage of time DC is operated on renewables at different solar and wind capacities at three selected Meta's data centers in Oregon, Utah, and North Carolina. An intersection of the black lines show the current megawatt renewable investment amounts of Meta. So as you increase the deployments, you get diminishing returns in terms of renewable coverage or operational footprint. And in fact, if you try to reach 100% renewable coverage, there's a long tail to get there using only renewables. So to see the full length of the tail here we see the flattened versions of the previous plots with sum of wind and solar power shown as total renewable capacity on the x-axis. And the tail is the longest for Oregon because there are a significant number of days with very low wind power. And for solar only regions like North Carolina, the highest renewable coverage you can get is around 50%. And hybrid regions like Utah, the tail is shortest since solar and wind has somewhat complementary generation profiles. And the tails discussed here are to mitigate the operational footprint, but there's also the embodied footprint coming from the building part themselves. Later, we will see how Carbon Explorer helps determine the optimal investments by taking into account both. Next solution we included in Carbon Explorer is battery deployment. We use a simple data center side lithium-ion battery model where batteries are charged when there's excess renewable supply and they are discharged when there's lack of supply. And with battery deployment, hourly renewable coverage increases, but there's additional carbon costs coming from manufacturing and other environmental effects too. Carbon Explorer analyzes how much battery capacity you would need for different renewable investment amounts. And the values in the grid shows the battery capacity in terms of hours data center would need to operate fully on renewable energy. Next solution we implemented in Carbon Explorer is carbon-aware scheduling. With carbon-aware scheduling, you shift or delay workloads in the data center from times where there's lack of supply to times with excess supply. And figure here shows an illustration of our algorithm where you have a maximum allowed capacity and a flexible workload ratio. And within these constraints, you shift the workloads from times when carbon intensity is high to times when there's low. As this requires workload flexibility, AI training workloads are great candidates as majority of them happen online and usually long-running jobs. And for Google, Borg traces show that about 40% of the workloads in Borg have flexibility to complete within a day. Now we need to put together all of the solutions and include the embodied footprint of the hardware in the picture. When calculating the embodied footprint, we take into account their lifetime. For example, servers last about 4 or 5 years, batteries 1,000 cycles, and renewables 25 to 30 years. And here's the total footprint analysis Carbon Explorer outputs. The bar charts show the carbon optimal points in all of our data centers across the US. The hashed parts of the bars shows the embodied footprint, and the solid portion of the bars is the operational footprint. So existence of a solid portion means that the optimal solution was not to reach 100% renewable coverage. And optimal renewable coverage is shown as red labels on the top of the bars. So if it's 100% optimal, you'll see a green star. And so renewable coverage of the optimal solution ranges from 46 to 99% for different regions using a renewable only solution. And it's not 100% in any of the cases. And note that the footprint on the x-axis here is normalized per megawatt of data center capacity. That means we can also compare across regions and determine which region is better suited for renewable energy availability. And that can be used for data center site selection. And for example, Nebraska, Utah, and Texas data centers are best options to optimize for 24/7 renewable coverage. Next, we add battery on top of renewables. With this solution, you see that solid portion of the bars are completely disappeared in all regions except 2 of them. That means the most optimal way to deploy batteries in most cases is to deploy enough capacity to remove the operational footprint completely. And overall, batteries enables an order of magnitude or more reduction in total footprint. Finally, a renewables and carbon-aware scheduling solution provides a competitive strategy to achieve carbon reduction too. The additional required server capacity for scheduling is in the range of 1 to 11% for these regions. So it means if we deploy additional servers, that can actually help reduce the overall footprint by doing carbon-aware scheduling. But on the other hand, for solar-only regions, since scheduling is limited by the degree of workload flexibility and relies on additional server capacities, scheduling alone is not sufficient to reach 100% renewable coverage. This is also the case for regions like Oregon, where wind generation is not as consistent compared to other regions. So overall, this is the approach we use in Carbon Explorer to help evaluate potential solutions to complement renewables. And going forward, we are implementing a combined battery and carbon-aware scheduling solution in Carbon Explorer 2. And I have shown you the steps we need to take to have a holistic approach, which is to include both embodied and operational footprint and use fine-grained hourly data. And I also show practical examples of using Carbon Explorer as in our data centers as case studies too. So if you're interested in experimenting with data center design like this, Carbon Explorer is open sourced on GitHub. We also have an archive paper in submission if you're interested in learning more. We would like to enable more solutions and better models to be plugged in and evaluated on this framework. So with that, I'll take a moment to thank my collaborators and conclude my talk. Happy to take questions.
Thank you so much, Bilge, again for your great talk, and sorry again for those interruptions in the middle. I think we are in good shape right now. And so we are running a little bit out of time, but if there are some questions, please feel free to ask. Philip, go ahead.
Hey, cool. Yeah, thanks a lot for the talk. I was having one question regarding the carbon-aware scheduling. So I was wondering which metric you actually optimize towards, because you wrote carbon intensity. So is that like the carbon intensity of the entire grid, or do you have like some more knowledge about, like, I mean, you for sure have some power purchase agreements and exactly know who are your power providers and stuff. So do you optimize towards the global grid?
Yep, very good question. We actually have 2 modes. We have an option where we look at the carbon intensity of the grid using all of the energy sources. That's one option. The other option we take is we project the energy output coming from our power purchase agreements. So an estimate how much exactly hourly renewable, how much hourly renewable energy they will produce, and use that as a second option too.
Okay, cool. Yeah, interesting. Thanks a lot. But this is on you. Like you have to project how much they will provide at what point in time. So this is no data that they provide to you.
Yes, no, we projected ourselves in this work. And we do that looking at what is the hourly generation of the grid as a whole. And while this is just the data is coming from the local grid, not that particular solar farm we built, but it's a close enough approximation, I think.
Yeah, okay, cool. Thanks a lot.
Thank you. I'm happy to answer more questions in the chat if we are out of time.
We can have one more question. I see one more hand here raised. So Alok, please go ahead and ask the question.
Thank you. Yeah, excellent talk. I mean, this is super interesting. But one question that I had was around the battery modeling that you did, right? You were able to offset all of the operational carbon with the battery modeling, but the limit of 1,000 cycles combined with that kind of, because the data center lifetime is what, 10 to 15 years, how do you kind of balance that with the battery lifetime as well?
Yeah, so we assume a simple lifetime model. We assume one charge discharge cycle will be used per day, which is true for solar only regions. That will happen. But wind only regions, the lifetime of the battery, it will be more complex because how you charge and discharge will change the lifetime. Our current assumption is just you will use one charge discharge cycle, one cycle per day. And as the framework looks at within a 10-year lifetime of a data center, how much battery you would need. So since server lifetime is 4 or 5 years, within a 10-year period, you need to replace your servers like twice. So we take that into account, and we proportionately project the embodied footprint based on normalizing the lifetime to 10 years.
Makes sense. Yeah, thank you so much.